Classics of the kitchen. Modern household cleaners remove dirt and stains. A not-so-secret ingredient is ammonia, one of the most common bases. Acids are the opposite of bases. Acid stomach, acid brain, acid in your drink. Acids and bases neutralize each other.
Wow, look at the bubbles.
What are acids and bases? This base ranks 5th on the list of most produced chemicals. It's lime, calcium oxide. Farmers use it to neutralize acids in soil. Like ammonia, lime cleans up. It's used to precipitate impurities from sewage. Lime is one chemical that can be dumped. Dumped into rivers in coal mining country, it will reduce acidity. And dumped into coal-burning power plants, it can neutralize 90% of the acidic pollutants that could escape into our atmosphere. Acids. Strong acids are essential in industry as reactants and catalysts. Sulfuric acid in batteries is very corrosive. Strong acids are dangerous and must be handled carefully. Some weak acids are familiar to us. Citric acid is a weak acid and is found in many beverages, in plants, and of course in citrus fruits. Apples can be fermented to produce the weak acid, acetic acid, found in vinegar. Such acids are found not only in the natural world, they can also be manufactured. Acids and bases, then, differ widely in their properties. Let's examine these differences in the laboratory. Acids change the colors of dyes, such as litmus. Acids produce hydrogen gas when reacting with metals such as magnesium. Acids produce gaseous carbon dioxide when reacting with limestone. Bases do not react with magnesium or limestone. Acids and bases are opposite. They react to neutralize each other.
What would happen if we mixed acids and bases? Let's try this one. I'm just going to take these tops off. Put the tops together. Look at the smoke. It's definitely a reaction, huh? How about this pair? Geez, nothing exciting there. I don't see anything happening. How about this pair? Wow, look at the bubbles. Now, those three reactions certainly were different, but what do you think these reactions have in common?
The ammonia and the hydrogen chloride react to form a cloud of solid ammonium chloride. Nitric acid reacts with sodium hydroxide to form soluble sodium nitrate and water. Acetic acid reacts with sodium bicarbonate to form carbon dioxide gas, water, and soluble sodium acetate. Chemists can use equations to identify similarities. Consider these equations for the three reactions. The reactions still appear different, but look closer. In all three, hydrogen ions, or protons, play a role. Proton transfer is the common factor. Let's look at the reaction on a molecular level. Focus on a single molecule of hydrogen chloride and a molecule of ammonia. Here, hydrogen chloride acts as an acid, donating a proton. Ammonia acts as a base, accepting a proton. A proton is transferred.
What a heartburn. How do you spell relief? Check the board, Coach. R-O-L.
The reaction of an antacid, a base, with stomach acid is an example of neutralization or proton transfer.
The stomach produces a small amount of acid all the time, but then that amount of acid may be stimulated by food. Even the sight and smell of appetizing food is enough to make the stomach produce more acid.
What actually happens in your stomach after you eat a meal? Both hydrogen ions and chloride ions move through the stomach lining from the surrounding blood plasma. In the stomach, these hydrogen ions produce a highly acidic medium. That is what it takes to activate certain enzymes for the process of digestion. But if the acidity of the stomach becomes excessive, problems can occur. Problems which often need an antacid solution.
There are a variety of different compounds that can function as antacids. For example, sodium bicarbonate could be used as an antacid, or magnesium hydroxide, calcium carbonate. There are a variety of compounds. Any antacid is as good as another at neutralizing acid.
Common acids and bases are solutions of compounds in water. Water plays an important role in transferring protons, as demonstrator Paula Heron will show us.
When hydrogen chloride is put into water, a proton is instantly transferred from the hydrogen chloride to the water molecule, producing the positively charged hydronium ion and the negatively charged chloride ion. In this case, water acts as a base. It accepts a proton. But when ammonia is added to water, something different happens. The water immediately transfers a proton to the ammonia, producing the positively charged ammonium ion and the negatively charged hydroxide ion. In this case, water acts as an acid. It donates a proton. Water can either accept a proton or donate a proton, depending on the type of molecule it reacts with.
Proton transfers also take place in pure water by itself. A molecule that receives a proton becomes a hydronium ion. A molecule that loses a proton becomes a hydroxide ion. The number of proton transfers in pure water is only 1 in 555 million molecules. That's equal to a concentration of 10 to the minus 7th moles of hydronium ion per liter of water. To express the concentration more simply, the minus sign is dropped and the power of 10 is used by itself. This number is called the pH, so water's pH is 7. How can we measure pH? One way is with an instrument called a pH meter.
It works on the principle of an electrochemical cell. It consists now of this meter that gives us a number readout and this electrode which measures the concentration of hydronium ion in solution.
Here is a range of solutions of differing acidity. When the concentration of hydronium ion is 10 to the minus 1, the pH is 1. When the concentration of hydronium ion is 10 to the minus 2, the pH is 2, and so on. If the concentration drops to 10 to the minus 7, the pH is 7, the pH of pure water. The value of the pH becomes larger as the hydronium ion concentration becomes smaller. pH is a measure of the concentration of hydronium ions in water solutions. This chart shows the pH scale and the pHs of several common substances. A decrease of 1 pH unit means a 10-fold increase in hydronium ion concentration. What determines the hydronium ion concentration of a solution? Well, one factor is obviously the amount of acid or base per liter of solution. That is, the molarity. For example, A more concentrated acid solution will have more hydronium ions, and therefore a lower pH than a less concentrated solution of the same acid. But there's also a second factor that determines hydronium ion concentration: the nature of the acid or base itself, whether it's strong or weak.
One way to tell whether an acid is weak or strong is by the use of an indicator whose color changes depends on the pH of the solution. These test tubes contain solutions whose pH ranges from 1 to 12, from strong acid to strong base. This indicator changes colors from red to yellow-green. I have two solutions here. Both of them are the same concentration, 0.1 molar. This is nitric acid, one of the strongest acids I have in the lab. Let's see if we can find its pH. Let's see. Its pH is 1. Let's try the other acid. It has the same concentration, 0.1 molar. Let's see. Its pH is about 3. You want to know what this is? This is acetic acid, vinegar, a much weaker acid. What is it that makes one acid weak and the other one strong?
The answer is that weak acids produce only a few hydronium ions. Very few weak acid molecules break apart into ions and donate their protons to water. But strong acids produce many hydronium ions because they break up completely in water. So the pH of a weak acid will be higher than a strong acid's, even though the molarity of the two may be the same. The pH of rainfall is now a major concern. In some areas, the rainfall is as acidic as vinegar and has even reached the pH of battery acid. The normal pH of rain is about 5.6. It is made acidic by carbon dioxide produced by forest fires and sulfur dioxide from volcanoes. But humans are responsible for lowering the pH even more. Emissions from cars, trucks, and planes contain oxides of nitrogen. Sulfur dioxide is produced when coal is burned for power and industry. Both sulfur and nitrogen oxides dissolve in water to make rainfall acidic. Midwestern oaks, maples in the northeast, the proud ponderosa, all are damaged. Leaves and needles are lost. Shoots appear crooked, deformed. Leaves turn out discolored and abnormally small. Lakes are threatened by a change in pH. Some lakes are able to absorb changes in acidity quite well, but others are becoming irreversibly acidic, and the damage to life is severe. A worldwide effort is being made to reduce acid rain. It's a real-life opportunity for scientists to apply their knowledge of proton transfer, the chemistry of acids and bases.